Hello guys, this is George Kamiti. Welcome back to our channel. And today we are analyzing composite materials. And we got this question down here that says this. A steel bolt and sleeve assembly is shown in the figure below. The nut is tightened up on the tube through the rigid end blocks until the tensile force in the bolt is 40 kilonewtons. If an external load of that kilonewtons is then applied to the end blocks, tending to pull them apart, estimate the resulting force in the bolt and the sleeve. So, on this diagram here, we got the nuts at the end of this whole component. Then we got the end blocks. And then this shaded region represents or shows the steel sleeve with an external diameter from this region to this one of 62.5 millimeters, internal diameter of 50 millimeters. We got a bolt. This is a bolt with a diameter of 25 millimeters. The length of the steel sleeve is 400 millimeters, and the length of the bolt is 500 millimeters. Now, we are going to begin with determining the cross-sectional area of the bolt as well as that of the steel sleeve. Now, let's begin with determining the cross-sectional area of the steel bolt. And therefore, the cross-sectional area of the bolt will be given by pi over 4 multiplied by the square of its diameter. And this is going to be pi over 4 times. The diameter of the bolt is 25 millimeters. Convert that to meters. 25 divided by 1,000. And that gives us 0.025 squared. And when we do that, we are going to get the cross-sectional area of the bolt being 4.9 times 10 raised to the power of negative 4 square meters. Therefore, that is the cross-sectional area of the bolt. From there, we determine the cross-sectional area of the steel sleeve. And in this case, it will be given by pi over 4d squared, that is the square of the external diameter, minus pi over 4d squared, that is the diameter, that is the internal diameter. So the external area minus the internal area. We can factor out pi over 4, and when we do so, we are going to have pi over 4 into d squared minus d squared. So from there, we are going to have the area of the steel sleeve being equal to pi over 4 into external diameter 62.5 millimeters. Divide that by 1,000. Divide 62.5 millimeters by 1,000 to convert it to meters. And that is going to give us a diameter of 0.0625. Then we square that. Minus internal diameter is 50 millimeters. We convert it to meters. That is going to be 0.05 meters. Therefore, 0.05 squared. And this is going to give us an area of 1.1 times 10 raised to the power of negative 3 square meters. Therefore, that is the cross-sectional area of the steel sleeve. Now, from there, we are going to determine the stresses that will be developed in both the bolt as well as the steel sleeve after tightening the nut through the rigid end blocks until a tensile force of 40 kilonewtons is attained or is achieved. Now, in this case, we know that stress is given by load over cross-sectional area. Therefore, here we are going to have this, the stress due to tightening. The stress due to tightening the nut. Tightening the nut. Now, we are going to determine the stresses that will be developed in both the bolt and the sleeve after the nut has been tightened all the way up to a load of 40 kilonewtons. Now, we know that stress is given by load divided by cross-sectional area. Therefore, starting with the stress that will be developed in the bolt, we are going to take the load divided by the cross-sectional area of the bolt. And in this case, this is going to be 40 kilonewtons divided by cross-sectional area of the bolt is 4.9 times 10 raised to the power of -4. And that is going to give us a stress in the bolt, a stress of 81,632.65 kilonewtons per square meter. Then the stress that will be developed in the steel sleeve will be given by the load of 40 kilonewtons divided by the cross-sectional area of the steel sleeve. And in this case, the load is 40 kilonewtons. Cross-sectional area of the steel sleeve is 1.1 times 10 raised to the power of -3 square meters. And this is going to give us a stress in the steel sleeve, a stress of 36,363.636 kilonewtons per square meter. And in this case, this is going to be a compressive since the steel sleeve will be compressed, but the bolt will extend. Now, we now have the stresses that will be developed in both the bolt and the steel sleeve after the nut is tightened up to a tensile force of 40 kilonewtons. Now, from there, we are going to determine the stresses that will be developed in both the bolt and the steel sleeve after an external load of 30 kilonewtons has been applied on the end blocks. And in this case, let's have these stresses developed due to a tensile force of 30 kilonewtons. Due to a tensile force of 30 kilonewtons. Now, from this relation, that is from the equilibrium equation, we know that the load shared by the bolt plus the load shared by the steel sleeve will give you the total load. And we know that from stress is equals to load over cross-sectional area. When you make load the subject, we are going to have load is equals to stress multiplied by cross-sectional area. Therefore, the load shared by the bolt will be given by stress developed in the bolt multiplied by the cross-sectional area of the bolt plus the load shared by the steel sleeve will be given by the stress developed in the steel sleeve multiplied by the cross-sectional area of the steel sleeve, which will be equal to the total tensile force of 30 kilonewtons. Therefore, this tensile force of 30 kilonewtons will be shared by both the bolt and the steel sleeve. Now, we are now going to have the stress in the bolt times the cross-sectional area of the bolt, which in this case is 4.9 times 10 raised to the power of -4. We add that to the stress developed in the steel sleeve multiplied by the cross-sectional area of the steel sleeve, which is 1.1 times 10 raised to the power of -3 will be equal to the total force of 30 kilonewtons. 30 kilonewtons. Now, from there, we know this, that the Young's modulus of elasticity is given by the ratio of stress to that of strain. So when we make strain the subject, we are going to have this. Strain is equals to stress divided by the Young's modulus of elasticity. When a lot of 30 kilonewtons is applied on the end blocks, what will happen is that strain will be developed in the bolt as well as in the steel sleeve. And in this case, the strain that will be developed in the bolt will be equal to the strain that will be developed in the steel sleeve, because this is a composite material. And therefore, when we begin with the strain in the bolt, we are going to have the strain in the bolt will be given by stress developed in the bolt divided by the Young's modulus of elasticity of steel. The bolt is also a steel, it is a steel bolt, it is made from steel. On the other hand, the strain in the steel sleeve will be given by stress in the steel sleeve divided by the Young's modulus of elasticity of steel. We know this, that strain is given by change in length divided by the original length. It is given by that. And therefore, we can say this. The strain in the bolt will be given by changing length of the bolt divided by the original length of the bolt, which will be equal to the stress in the bolt divided by the Young's modulus of elasticity of the bolt. And in this case, when you make changing length the subject, we are going to have this. Change in length in the bolt will be equal to stress developed in the bolt divided by the Young's modulus of elasticity of steel multiplied by the length of the bolt. Likewise, the change in length in the steel sleeve will be given by stress in the steel sleeve divided by the Young's modulus of elasticity of steel multiplied by the length of the steel sleeve. So, the changes in lengths in both the bolt and the sleeve are going to be equal because the strains are equal, and strain is changing length divided by the original length. Therefore, the change in length in the bolt is equal to change in length in the steel sleeve. So let's equate their formulas. We are going to have stress in the bolt divided by the Young's modulus of elasticity of steel times the length of the bolt is equals to stress in the steel sleeve divided by the Young's modulus of elasticity of the steel sleeve times the length of the steel sleeve. Now, the Young's modulus of elasticity is going to cancel out because it is equal. We are talking about the same material, that is steel. Therefore, we are going to have this relation. Stress in the bolt times the length of the bolt is equals to stress in the steel times the length of steel. So when you make stress in the bolt the subject, we are going to divide both sides by the length of the bolt, divide this side as well with the length of the bolt. Now, this one will read as to stress in the bolt will be equal to the stress in steel times the length of the steel sleeve is 400 millimeters from this point to this point. So that will be 400 divided by the length of the bolt is 500 millimeters. So we divide that by 500. And this is going to give us stress in the bolt will be equal to 400 divided by 500, that's going to be 0.8. and therefore the stress in the bolt will be equal to 0.8 stress in the steel sleeve. So this relation, we are going to use it in a few. Now, coming back here, the stress in the bolt, that is at this point, the stress in the bolt is 0.8 stress in steel. Therefore, we are going to have this 0.8 times the stress in steel multiplied by the cross-sectional area of the bolt, which is 4.9 times 10 raised to the power of -4, plus the stress in steel multiplied by 1.1 times 10 raised to the power of -3 is equal to the total tensile force of 30 kilonewtons. Now 0.8 times 4.9 times 10 raised to the power of -4, that will happen to be 3.92 times 10 raised to the power of -4 stress in steel plus 1.1 times 10 raised to the power of -3 times the stress in steel is equal to that. Now, when we add this to 3.92 times 10 raised to the power -4 stress in steel plus 1.1 times 10 raised to the power -3 stress in steel, that is going to give us 1.492 times 10 raised to the power of -3 stress in steel is equal to 30. Then from there, we are going to divide both sides by 1.492 times 10 raised to the power -3. Divide this side as well by 1.492 times 10 raised to the power of -3. And that is going to give us a stress in steel, a stress of 20,107.24 kilonewtons per square meter. So that is the stress that will be developed in steel. On the other hand, the stress that will be developed in the bolt, stress in the bolt will be equal to 0.8 times the stress developed in the steel, which is 20,107.24 kilonewtons per square meter. And that is going to give us a stress of 16,085.79 kilonewtons per square meter. So that is the stress that will be developed in the bolt. We are being asked to determine the what? We are being asked to estimate the resulting force. So what we are going to do, we are going to determine the resulting stress. Now, starting with the resulting stress in the bolt. So the resulting stress in the bolt will be given by the stress in the bolt due to tightening the nut. We can write due to tightening the nut plus the stress developed in the bolt due to application of a tensile force of 30 kilonewtons. That will be the resulting stress in the bolt. And therefore, since both the stresses are tensile, that is the stress due to tightening of the bolt is a tensile stress, and the one that has been developed due to a tensile force is also a tensile stress. We are going to add the two stresses, and therefore we are going to have 81,632.65 plus the stress due to application of a tensile force of 30 kilonewtons. So we add 16,085 0.79. Now, when we do so, we are going to get the resulting stress in the bolt, being equal to 97,718.44 kilonewtons per square meter. So that is the resulting stress in the bolt. From there, we are going to determine the resulting stress in the steel sleeve, and this will be given by the stress in the steel sleeve due to tightening the nut plus the stress in the steel sleeve due to application of a tensile force. And in this case, the stress developed in the sleeve due to tightening the nut is a compressive force of 36,363.636, whereas the stress developed in this steel sleeve due to application of a tensile force of 30 kilonewtons is tensile. This one is tensile as well. Therefore, since this one is compressive, whereas this one is tensile, those two stresses, the resultant stress will be this stress minus this one. Since one is compressive, the other one is tensile. So you're going to have that 6,363.636 minus 20,107.24, and that is going to give us a resulting stress in the steel, sleeve, a stress of 16,256.396 kilonewtons per square meter. So that is the resulting stress in the steel sleeve. Now, the question is asking us to estimate the resulting force. So I'll try to squeeze this here. Therefore, the resulting force in the bolt will be given by stress in the bolt, resulting stress in the bolt times cross-sectional area of the bolt. And in this case, the resulting stress in the bolt is 97,718.44 times cross-sectional area of the bolt, which is 4.9 times 10 raised to the power of -4. And that is giving us a force of 47.88 kilonewtons. 47.88 kilonewtons. So that is the resulting load or resulting force in the bolt. The resulting force in the steel sleeve will be given by the resulting stress in the steel sleeve times cross-sectional area of steel. And that's going to be a stress of 16,256.396 times cross-sectional area 1.1 times 10 raised to the power of -3. 1.1 times 10 raised to the power of -3. That is going to give us a load in the steel sleeve, a load of 17.88 kilonewtons. So that is the load that will be subjected to the steel sleeve. Therefore, ladies and gentlemen, we are through with our question. If it has been of benefit to you, please consider subscribing to this channel, and we are going to appreciate so very much. So thank you. Let's meet in yet another lesson.